This lesson is extremely important, everyone, so take very good notes. This lesson is about intermolecular forces, and we'll define what that actually means, and I'll be able to discuss with you dipole-dipole attractions and hydrogen bonding, which I'll circle in red right now because it's a very important intermolecular force. And we'll also use our knowledge of electronegativity to determine the strength of hydrogen bonding between differing substances. There is a bookwork associated with this lesson, 45 through 50 on page 112. We will do those in class. And when you make your classwork section of your notes today, please copy this aim. What is intermolecular force? And below that, you can also copy down these particular do now questions, which we will answer in class. So, to define intermolecular force, you may actually know the Latin root inter, which would mean between, and molecular, of course, molecule, and force is a push or a pull, and in this case specifically it's a pull. So intermolecular forces are forces of attraction between molecules. So I'm going to try to explain what causes intermolecular forces before I explain why they're actually extremely important. The type of covalent bonding that you'll see in the diagram below is polar covalent bonding. And the way that you can tell that is that you have this unequal distribution of electrons within the molecules. And you can see that they have arranged themselves in one particular way, which is that we have the slight positive end of one molecule being lined up right next to the slight negative end of a neighboring molecule. And you can see that this pattern continues throughout the chain, slight negative versus slight positive, and again, slight negative versus slight positive. The reason why that happens is because of the electrostatic attractions between positive and negative ends of neighboring molecules. So when you combine this idea of electrostatic attractions between positive and negative ends of neighboring molecules and the definition of intermolecular force itself, which is a force of attraction between molecules, then it shouldn't be so difficult to see that the area where intermolecular force is acting is here, between the, I think we could call them poles of neighboring molecules. And since this force is primarily an attractive force, one that pulls molecules together, this will have an effect on the melting point and the boiling point of substances. I'm going to pause the video now, and I will give you options to choose whether you think that it will increase the melting point, decrease the melting points, or have no effect on the melting points and boiling points of substances that have intermolecular forces. So the presence of intermolecular forces between polar covalent molecules actually will increase the melting point and the boiling point for that substance, especially compared to a substance of similar molecular weight, but who is non-polar. And the reason for that is because those attractions between these polar molecules will make them resist being pulled apart. And when you really think about melting and boiling, what you're really doing is you are separating molecules from one another. And that is going to be much, much more difficult in a substance where molecules have attractions for one another. So one type of intermolecular force which is considered relatively general is called a dipole-dipole attraction. And a dipole is just a molecule that has two poles. Greek root di would just mean two, and pole, it means pole, so two poles. And another way of referring to a dipole is, of course, a polar covalent molecule. The formation of a dipole, aka a polar covalent molecule, is caused by an unequal distribution of electrons which results from an electronegativity difference between the atoms involved in the bonds. Therefore, dipole-dipole attraction is actually just an attractive force between dipoles. And another way that you could refer to this is what the regents would call it, and that would simply be intermolecular force. And the root cause of the formation of dipole-dipole attractions, or intermolecular forces, is in fact the unequal distribution of electrons. So I have highlighted that here. We have the unequal sharing of electrons, which is causing the dipole formation itself. And then those opposite poles that are created by the unequal distribution of electrons, those opposite poles actually will attract one molecule to another. And as we have discussed, that attraction has effects on the substance as a whole, meaning it can increase the melting point and increase the boiling point of the substance. And this leads us to a very special type of intermolecular force, which is called hydrogen bonding. Hydrogen bonds are intermolecular forces. I think that's an important thing to remember. And it results between the hydrogen atom of one molecule and the more electronegative element of another molecule. And specifically, that more electronegative element, which I'm underlining in blue, according to the regents, and this is not a nationwide or global definition, but according to the New York State regents, that other more electronegative element has to be one of only three. And those three are nitrogen, oxygen, and fluorine. No other element would be considered hydrogen bonding by the New York State regents. So the diagram here helps to illustrate this. We have the hydrogen atom here of one molecule, and we have an attraction between it and the more electronegative element of another molecule. And again, according to the New York State regents, this must either be nitrogen, oxygen, or fluorine, NO or F. And in this particular case, it is, of course, oxygen. You probably recognize these molecules in the diagram. These are molecules of water. So hydrogen bonding only occurs in polar molecules, such as the water molecules in the diagrams at left, and the reason why it has to be polar is because it is relying on intermolecular forces of attraction between poles of neighboring molecules, a slight positive end, which will be hydrogen, and the slight negative end, which would be either nitrogen, oxygen, or fluorine. So I used the Greek symbol delta, which we use in chemistry as slight. So it is between the slight positive and slight negative of those poles. So if you want to decide if you will have hydrogen bonding between molecules, one thing I strongly recommend is drawing Lewis dot structures to reveal whether or not the molecule has the asymmetry it needs to create attractions between two polar molecules. So I'm going to pause the video, at least for myself, and I'll draw some Lewis dot structures for these 5 molecules, and then we will determine together whether or not they have hydrogen bonding. Alright, so I went a little bit extra on many of these molecules. I not only drew their dot structure, which is going to be in black for each molecule, and being careful to include non-bonding electrons, but I also indicated using the Greek letter delta, whether each of the atoms was considered a slight positive or a slight negative pole. And the way that I decided that, just by the way, was I chose the more electronegative element to be the slight negative pole, and then the other element would be slightly positive. So I'll write that in now. So since this molecule is polar, it has slight positive and slight negative ends, then if you introduced another molecule that was polar, you would have attractions between these molecules. So you definitely would have dipole-dipole attractions, no question at all. But the strict definition for hydrogen bonding is the attraction between the hydrogen of one molecule and the more electronegative nitrogen, oxygen, or fluorine of a negative molecule. Unfortunately, sulfur does not meet that definition. So hydrogen bonding in this case, no, it would not be hydrogen bonding, but it would be considered dipole-dipole attraction. So on to the next one. Again, we have our polar molecule, so we will definitely have dipole-dipole attractions. And this one also meets the requirements for hydrogen bonding. So yes, hydrogen bonding. And here we have ammonia. It definitely meets the requirements for dipole-dipole attractions. So the molecule is polar, it would attract a neighbor that was also polar. And since the more electronegative pole is nitrogen, oxygen, or fluorine, nitrogen in this case, then it meets the requirements for hydrogen bonding. The next molecule is hydrogen fluoride or hydrofluoric acid, and it meets the requirements for dipole-dipole attractions, and it also meets the requirements for hydrogen bonding because fluorine is the more electronegative pole. And on to my last example, I have hydrogen chloride or hydrochloric acid. It does meet the requirements for dipole-dipole attraction because of its polar structure being able to attract neighbors, but it does not meet the technical requirement in New York State for hydrogen bonding, in that the more electronegative pole, chlorine, is not nitrogen, oxygen, or fluorine. So, in order to determine the strength of hydrogen bonding between several different molecules such as hydrofluoric acid, hydrochloric acid, hydrobromic acid, or hydroiodic acid, what we need to consider is actually probably something you could guess. You would have the most attraction between molecules of hydrogen fluoride or hydrofluoric acid. So if you had one here and another one here, you would get the strongest hydrogen bonding in this molecule, and the reason is that it has the largest electronegativity difference between the hydrogen atom, which is the slight positive pole, and the fluorine atom, which is the slight negative pole. So in other words, the slight positive pole of this molecule and the slight negative pole of this molecule are going to have the largest imbalance in charge, and therefore this will be the most negative of all of the negative poles, and this would be the most positive of all of the positive poles, and therefore you would have the greatest attraction between two molecules of hydrofluoric acid. So I labeled the slight negative and the slight positive portion of each molecule. Well, I'll do that now, actually. And the molecule which would have the most polar character would be HF, because it has the largest electronegativity difference. HF would also have the strongest hydrogen bonding because it has the largest electronegativity difference. But the lowest boiling point would go to this molecule of the four that we have, hydroiodic acid. And the reason is because it has the smallest electronegativity difference between the hydrogen and the iodine portions of the molecule, and therefore you're going to have the weakest positive pole and the weakest negative pole of all of the four molecules. And when you introduce another hydroiodic molecule next to it, you would also have the weakest attraction and therefore the lowest boiling point. And so I wrote, you would have the weakest positive and negative poles because of the smallest electronegativity difference between H and I. And so we've done it. We've reached the pair up. Please copy down these four molecules. There is some very odd formatting here. We can correct it tomorrow when I display these on the board. But this is H2S, CH4. These should be subscripts. And they're also answer choices, of course. And these are subscripts as well. And then this one should be decently formatted. So copy these down. Also, please copy down these summary questions, many of which are definitions, but these definitions are extremely important and the Regents test them all the time, so I want them in your summary. Thank you for listening.